Who's there? Come on in. Avery, how you doing? Good to see you. Well, hope everything is going well for you. We've got a good lecture today. Not really a lecture, it's a lesson, but we've got a few demos that we're going to do. And we'll give it a try. Let's first, since it's been a couple of days, refresh what we've been doing. The first thing I want to say is the essay that you sent back on describing the functions and how a steam engine works was just very, very good. It was great. Well done. You even added in the safety valve, which I didn't even think about and I'd forgotten, but you described very well on how to get from a source of energy in the wood or the coal into the tank to make steam to make the engine work. That was very, very good. Well, where have we gone up till today? We started out with states of matter. That's what led us to the steam engine. When we talked about solids, heating them up, liquids, heating that up to get to steam and vapor. And the more energy we put in through maybe the coal or the wood or whatever, the more energy that was absorbed in the fluid. And that's what happened to the steam when we wouldn't let it expand in that container. We blew it out and we ran a little tiny machine with it, just like you ran the steam engine. And that little machine showed us how we can develop pressure if we keep the volume the same. It also showed us that if we use that steam coming out, as they do in a power plant, we can generate electricity, like a lot of the power plants do here. And that led us to the discussion of converting energy from that thermal energy, where we heated up the steam, and we converted that to mechanical energy, turning something. And if it's a generator we're turning, we then convert that one more time to electrical energy, and we can send that out over the wires to all the houses, and that's the little electrons running in those particular wires. Or we could save it. We could store it in a battery and use it later on if we wanted to. And that led us to other discussions on when we got into those machines, into simple machines. And you did a great job in describing all the simple machines you found by going through your barn, your house, your yard, and all those particular things. There's a lot of them out there, and you'll see them every day as you travel around. From doorknobs to inclined planes to wedges to knives and to an opening of a bottle or a screw going into a wall. So there's a lot there for simple machines. And those simple machines can be added up together, like we did on that coverall I had. I think we had a lever in there, we had a wheel and an axle in there, I had a wedge in there. There's a whole bunch of those things. So we discussed all that electrical pieces and the electrons and the generators. And that led us to the energy that came from electricity, the electrons going through a wire that produced a magnetic field around the wire. And if you remember, I showed you that that could interfere with a compass because there was a magnetic force. And that magnetic force we can use to build another machine called a motor. So if we put electricity through a wire, coiled it all up, and then that wire rotated inside a magnet, we would have the motor would continue to run. And if we did it in reverse, like if we put somebody on a bicycle that was pedaling and moving a generator, we produce electrical. So I thought that was pretty good. So here we are. Today we're going to do what I'm going to call lesson 5 and 6 together, because I spent a lot of time on the electricity and I've got to get us back on track with what we originally said. And what we're going to do today, we're moving from sound into light. And then we're going to go on into a spectrum of light, what comes out of the sun, and we'll get into vision and color and reflections and refractions and things of this nature, and then into lenses. Then our next lecture, which will be lecture 7, we're going to talk about the Earth. We'll start talking about the Earth and volcanoes and how it's made and the earthquakes and the rocks and things of this nature. Oh, it should be very interesting. I'm looking forward to that. Now, the most important thing from our discussions on sound was the fact that all sounds are created and caused by vibrations. And you sent me a homework assignment from lesson 3, or maybe it was lesson 4, but it was very, very good. You gave me the sounds of the orchestra pieces. A trumpet player vibrates their lips. A violin player does it with a bow. A harp does it by plucking. A saxophone or a clarinet does it by, there's a little reed in the mouthpieces that vibrates and fluxes. Everything has to vibrate to make sound. And what happens is when they vibrate, these little particles in the air bounce against each other, and then they go out as a wave. Just like the wave in an ocean, after it hits a rock, it comes down and the waves come this way. And we described those particular pieces through several ways. Now this I showed you last week. These are the waves going by, and there's 2 waves here. The blue wave has got a higher amplitude, which means it's louder. And the red wave is a little softer, a little quieter. And that's the amplitude. So you can make a trumpet be really loud, or you can make it be really soft, but it'll play the same note. And every individual note has the same frequency. Now, frequency is probably hard to understand. And I described it when we first started talking about going to the kitchen. If you go there frequently, that's a high frequency. If you don't go there too often, like maybe the supermarket right now, that's a lower frequency. And that has an effect on sound, for instance, and then other things. Now, there's several waves here. The one on the top is a low frequency. As you can see, it only has 2 spots. It has 1 spot here and 1 spot there. That's low frequency. Where the one on the bottom is higher frequency. You can see all these. And those are waves. This is a high-pitched, like the top, the highest notes that you can play in a recorder. This would be lower. This would be the lowest one that you can do on a recorder. And then those sound waves wind up coming right down this little ear canal right here on the left side of this picture, through your ear canal, and then it bumps into the eardrum. That's the first red arrow that they have there, and make the eardrum vibrate. And those vibrations, just like if you were hitting the tabletop or something like this, you can hear it down the other end, goes through some bones, and then into that blue circles there, the cochlea. Inside there are fluids, and the fluids have little hairs that stick up. And as that water moves, or that fluid moves inside there, those little hairs are connected to a nerve that goes to the brain. And over a period of time, we learn what all these different sounds are. Right now, Will hears some of these sounds and doesn't know exactly what they are, but those impulses are going through his ear, through his drum and the bones, that cochlea, up into his brain, and eventually he'll hear it enough, he'll recognize it as a word, or a bird, or a door slamming, or something like that. And that's the way we learn. And remember, those are waves. Now, the first thing we're going to talk about is new today, but similar to sound. and that is light. Light is another form of energy. We had thermal energy that we used in the steam to turn turbines and make electricity and convert it to batteries and things of that nature. And then we had chemical energy, which is the food that you eat is converted to energy in your body, and leaves store up energy from the sun, and that's chemical energy that we use. We talked about potential energy, which is if I put a big heavy weight here, it's potentially can do some work, boom, and it crashes. And kinetic energy is moving that turbine. You don't have to worry about all that kind of stuff. But light is another form of energy. And we get several different sources of that energy. And the biggest source is what? I'll give you a hint. It only happens in the daytime. Yes, it's the sun. The sun produces a lot of energy, light energy as well. The sun is what they call nuclear fusion, but actually it's burning at a very, very high temperature. About 15 million degrees inside the very middle of it. It's about 5,000 degrees on the outside, I believe, or something like that. Yeah, and it burns hydrogen, converts it to helium, and then it releases all these waves, light and other waves that we're going to talk about in just a minute. So that's the sun. That's the predominant energy. In fact, there's so much energy in a square yard, which would be about 3 feet by 3 feet. There's enough energy in that if you had a 10-watt LED light bulb, it could light up more than 100 light bulbs in that one little place where we get the energy. So it converts to electrical energy through solar cells, which we mentioned last time, and I'll show you again in a couple of minutes what that is as well. The other source is electricity. Electricity can provide us light through a number of different ways, through light bulbs, LEDs, we'll talk about lasers, things like that, and we'll discuss that in just a particular section. And then chemical energy as such. A candle. A candle actually melts and converts states of matter, that wax that has got some vapors inside it. If we heat it up a little bit, and those vapors light on the top of a candle, and that's light for us and has been for years. Or burning oil is the same thing in a lamp. A firefly. Firefly is a chemical reaction inside that little lightning bug. It's not a fly, it's a beetle. And what it does is it has a chemical inside of it called luciferon. And we don't have it in our cells, but the lightning bug has it inside it. And when that chemical meets with oxygen, it glows. And it's interesting, there are some that will go either red, yellow, or green. Here we have a kind of a greenish yellow type. There's 2,000 different kinds of fireflies, and the ones on the West Coast, from what I understand, do not light up. And I'm really sorry about that. They also have their own flash patterns. All these 2,000 groups have different kind of flash patterns to attract each other. So those are some examples of how we make light. Now, first thing you probably ever saw or would note, or as will see probably sometime, is a shadow. And of course comes from the sun. But people for thousands of years have used those shadows to be able to tell what time it is. And I'm going to show you how we can do that. And Nona's going to come here in just a second. I'm going to call her in and see if she can come and help me produce that for you. 1 second, please.
Hi, Avery.
Now, what we're going to do, and Nona's going to help us here, is we're going to make a sundial. And it's a use of a shadow. And you'll be able to do it. We're going to make a fairly simple one so that you can tell. And we'll go through it. Nona's going to make it first. First of all, take a dish, like your mom might have. What's the name of that company that makes those real good ones up there? Pierce? Simon Pierce. Well,
Yes.
you take one of her Simon Pierce plates like this that's round, and you drill a hole in it. because we're going to stick a pest. Ooh.
Wait, you can't drill a hole in
Oh.
a Simon Pierce plate.
Okay, we better not do that. Okay, we'll
Okay.
put that aside.
All
And
right.
what we use is just a regular cardboard
Paper plate.
paper plate. We'll use a paper plate then. And if you don't have a paper plate like this, you can take just a piece of cardboard and make a circle using a compass or something like that. Make a nice circle and cut that out, as long as you know where the center of that is. Okay. Now Nona's going to mark the center. See, and every time you do this, you're going to have to pick this up there, and you can do it with it. Yeah. That's good. Okay.
Okay.
So mark a line all the way through, and make sure you know about where the center is. Perfect. Now we're going to go in a right angle, and you can pick up the triangle, honey. I want to show. Yes, I want to show exactly what a right angle is. And you can show the other one too. This little place right here on the end is straight up and down. That's called a right angle. It's 90 degrees, and it's what walls to a floor is and whatever. And on all different size, here's another one as well. So Nona's going to take
Let's use that one.
Okay, Nona's going to take this, and she's going to make a line straight up into about where the top. Yes.
Oh, like this.
Yeah. Now that's the reason we're doing is this. This is a right angle. It's also called perpendicular. It's a perfect thing. Right. Perfect. Okay.
X.
Good. Now on the very top, I would like you to put a little N. Ooh, I didn't want it right there, but that'll have to be okay. I wanted it on the edge so it gets out of your way. Well, that's okay. So we'll do it like that. Now, we want to put a hole in the middle of that.
Okay.
1 second. Now, I'm going to put a little hole in the middle of it. Get your mom to help you if you need that. Just be careful with that knife. Put a little, yeah, that's good. Not too big. Oh, just perfect. Perfect. Okay. Now we're going to take the pencil and stick it in from the bottom through, and so it sticks straight up in the air, right in the middle. Okay. Good. Okay. Now what we're going to do is we're going to see what happens when the sun comes up. Now, Nona has this this sundial corrected, and she will orient it when she puts it on the ground so that the N points north. And you use your mom's phone and check where the compass is and have this pointed down to the north. And then what happens is the sun comes up in the morning, and there is the shadow. Sun comes up on this side, so that would be about 6 o'clock in the morning, and the sun goes through the sky during the day. Here's about 9 o'clock, 10 o'clock. It's about noon. The sun keeps on going, and you can still see the shadow moves all the way around until the sun disappears. And that will be your sundial. Now let me show you one that we created here yesterday. This is the one we did, and we put it outside just to double check it. And you can see the north is there, so when you lay it down flat on a table, that would point to the north. And then the sun will come up in the morning and shine right there at about 6 o'clock. And you can check it. And as the sun goes, it'll be 7 o'clock, 8 o'clock, 9 o'clock, 10, 11, noon, 1 o'clock in the afternoon, 2, 3, 4, 5, 6 o'clock at night when the sun goes down. Now you can make this by using there you go. Now this little device has got all different angles on it, and we use it to draw angles. And if you put it right on Nona's piece right now, Nona has a hard time showing this, doesn't she? There you go. And if you mark off 15 degrees, every 15 degrees would be a time. So the first 15 degrees up would be 7 o'clock. the next 15 degrees, which would be a total of 30 degrees, would be 8 o'clock. And then the next 15 degrees is 45. Because I know you can do 15, 30, 45, etc., all the way around, and then get all the way up here where it's 90 degrees. And keep on going with those little marks. Remember, this is called a protractor. I think your mom probably has one. You might even have one in school. And around the edges of this protractor are degrees. So every different hour is a 15 degrees. So you'll start right over here at 6 in the morning because the sun's coming up from over there in the east. And then 15 degrees will be 7 o'clock, 8 o'clock, 9 o'clock. Every 15 degrees all the way around to the other side, where with the sun going down over here, the shadow will be there. So I'd like you to make one of those and put it outside and take a picture of it for me and send it back. And let me see here. This is what it should look like when you're finished. Let me see here. Marcia, give me a helping hand. There you go. Okay, thank you. And this is what it should look like. The shadow coming up in the morning from over there and the sun going all the way around. And you might have to move it around just a little bit to get it oriented and check it every day, but it should lay flat on a sunny area outside. Maybe tape it down just like this, because the sun's going to come up over here and it's going to go down like this and make your shadow. Good. I hope you make one. It should be fun and I'd like to see it. Not that hard to do. Okay, wire though goes across there, and electricity was forced through that little wire and caused it to heat up. And it heated up and it glowed. It glowed usually kind of a reddish yellow color, and that produced light for a long period of time. But it was not very efficient. By that I mean it actually made more heat than light. So it was it was very expensive to get light out of that particular thing. Also at that particular time, neon lights came in, and we'll talk about that fluorescent one in just a second that Nona has. But first there's neon. Neon is a light, and you see it in stores where they do advertisements and things of this nature. There's a gas inside that little neon tube, and as the electricity goes through and it's passed through the neon, it causes that gas to burn and cause a color. And neon itself is one of the chemicals that's inside it that'll produce red. So whenever you see a tube, it'll have red light with electricity going through it, and for some of those advertisements. The next light that came along is this fluorescent light. You see these in a lot of places, in stores. I have some in my barns and things of this nature. And it produces some light, and it's cheaper to operate than that old light bulb. Sometimes produces a nicer light, but it's a little dangerous because inside there is mercury gas vapors. And those gas vapors with a coating of fluorescent material on the inside of the glass causes that glow. And of course, if it breaks, you have to stay away from it. There's mercury gas in there, which is not good at all for us health-wise. The next piece I'll bring up here in just a second while Nona gets some other light bulbs. This one right here I showed you last week. This is a solar cell, and although it doesn't make light exactly, it takes the sunlight and the energy coming from the sun on a silicon plate that's coated and painted with phosphorus. Phosphorus has extra electrons, makes them move. And the bottom plate is boron, and it likes to have electrons, so it goes, all the electrons go to the boron, and we know what happens when electrons travel. That's electricity. So then we can take that electricity and use it for whatever we want. Electricity in the house, and running some of our small pieces of equipment, stuff like that. This is a solar cell. So using the solar energy from the sun, making electricity, and then converting it to light. Now Nona just showed you a fluorescent tube. Well, all of a sudden they came out with these CLFs, a curved fluorescent tube, or light, CLF. You probably have some of these around. This is the light that was replacing those old inefficient light bulbs I mentioned to you. And inside there also is that mercury gas and some fluorescent material on the coating of it. It still can be pretty unsafe, so you have to be careful with that. Along came LEDs. Here, Nona has a couple of examples of LEDs come in all different sizes right now. And they're plastic and they could be colored and whatever. And an LED has a name called light emitting diode. Don't worry about that. But it's something that takes electricity and sends it through some material called gallium. And what happens is it makes electrons move inside there. And when those electrons move, they discovered that it would produce light. And it doesn't produce hardly any heat. So it's very, very efficient, which means that we can get light very, very inexpensively. So we here, Nona and I, have changed all our light bulbs to these LED lights that we can use. But then again, the most important thing that we get is from the sun. Now, Nona is holding up a digital clock, and you can see it says 303. I think you can see that. And you might have one of those at home, and they are made from electricity lighting up a little diode. And each one of those numbers has 6 little diodes inside of it. Let me just show you what that looks like. Here it is here. Now, as you can see there, I drew this out on a little tiny, on a piece of paper. And there's several different little lights in there. And you see A, B, C, D, E, F, and G. And those are lights that are inside each one of those numbers. They're on your microwave just like that. They're on a lot of car radios. They're on clocks. And it's exactly like that. Now, if electricity goes to a couple of those light bulbs, let's say we sent one to A, F, G, E, and D. And we lit up each one of those individual diodes from an electric input, and we would get 3. Step back, you can see that that's a 3. And then if the next time we did it, if we added into it number B, we'd probably have maybe a 9, and we could change all these things. That's the way those digital clocks work, with a little bit of electricity going through one of those diodes. Now, there's one more thing that I want to show you, and then we'll come back to some more of this next time. In the next section, which will be next week, I'll add in reflection, and we have a giant mirror in the sky that reflects the sunshine and sends it back to us. You know what that is? It's a big mirror. It's about 240,000 miles away. It's the moon. It reflects the sunlight and sends it back to it's a giant mirror, and I'll show you how a mirror works. Then we'll talk about lenses, and we'll talk about how we can bend light and what happens to that. We'll learn how a magnifying glass works and things of that nature. Now here's something else that we're going to talk about next week as well. This is an eyeball. And what's taking place in the eyeball, just to show you, and I'll explain a little bit more. There's a little boy standing off to the left, and the light from this boy goes into your eye through where your iris is and your pupil is. And right behind that, where I put that blue arrow, is your lens. The lens focuses it on the back of your eyeball, and it shows it as upside down. And in that particular place are the receptors, the electrical hairs that collect that image and sends it to your brain on a nerve. And your brain knows it's upside down, but it tells you it's right side up. And then if you have, you can correct those lenses by putting something in front of it. Maybe a magnifying glass to see something bigger. Maybe a pair of glasses or something like that, or contact lens. And I'll show you how all those particular things work. And then also next week we're going to look at how does a laser work? How does a laser work? And we'll go into all of those particular pieces here. Well, let me check first of all. Let me check here. Yeah, first of all, see how our folks are doing out there. 1 second. Let's check with someone outside and see how they're doing, if they've enjoyed their lecture. What do you think about that? How do you think this is going? Is it going okay? Did you enjoy it? No? Tell me what you think. Oh, yes. Okay, I'm glad. Oh, she liked it. That's good. That sounds good. All right. Next time we'll do some more work on light. Just finish it all off. Talk about the light bulb and reflection and refraction, which is bending. Makes you it explains how you look so strange in some of those mirrors in different places. And then we'll go over the eyeball again one more time, and then we'll move on to the Earth. Now I have some homework for you to do. As I mentioned, I want you to make a sundial, and take as long as you want. And you can make a couple of them if you want. Remember, orient it so it's pointing north. And the 6 o'clock in the morning, as you look at it, will be on the left-hand side. And then the other thing I want you to take, I'm going to send you via email those digital little squares that are on clocks and things. I'm going to send you one so you can make a copy. And I'd like you, when we get together on FaceTime, to show me one of those with your age on it and one of them with Will's age on it. See if you can do those, okay? Well, that was good. Hope you're having a great time. And we'll see you next time. So thank you. Have a great day. Bye.